because that would be bad if we lost that. There is a way I could just set the meetings to automatically record. And I've told you that I intend to record all of them. You don't have to show your face or voice. I might just set the meetings to automatically record so I don't screw up. Okay, now let's go back to the website. I want to answer Maddie's question, and I want to answer, drum roll, number one question I received over the last 48 hours. So share screen, and I'll blow up this page so you can see it slightly better. You can go to the website yourself. Number one question I received over the last 48 hours is, what is our course number? And it is right there in the syllabus. And I want to be careful that I'm not misinterpreted, because you could think someone's trying to be a jerk. Every time someone's asked me that question, I sent them back a link to our course and said it's under the syllabus, under course, required materials, and XYZ homework. So I definitely want you to read the syllabus, and you pick up the course number here, create your account, log in, supply the course number, and then activate with the course code. I did have a couple other questions that said, you know, Delta College login was not working on XYZ homework. That is correct, because you have to create an account on the XYZ homework. Okay, so just trying to keep you informed right there. After today, I'm going to dive in to the XYZ homework and look at how many people I have, who's missing, who I might have to keep helping get in, but get as many of you in as you can. Get yourself in, then get your friends in. Okay, next question was from where do you find the videos that I've posted on my website? So let's just do it, you know, straight ahead fashion. So here's 121. Could be under resources. It is under resources. Could be under week one. Since we're in week one, let's try week one. Week one, video, class session video. So if you click on this August 31 right here, you are going to go to the class session video, which is posted on YouTube from Monday, August 31. And let me back up. If you want to see all the class session videos, of course, there's only one right now. Just go to that playlist. I don't know why you want to see the whole playlist, but there's a whole playlist. You know, if you want to search for something, that's good. And also, not much in there right now, but I established a playlist if I made a video of recommended problems. So here's first video of a recommended problem, and it was a little bit rough. I want to do an example where I show you something more just to practice this, because I don't like these spirals here. It's probably going to make you dizzy, but listen to it and tell me what you think. Okay, back. So in any week, you can find the videos associated with that week. As we go on, under resources, you can look at resources, video, and then the class sessions. I might have to reorganize the way I label that, but this will have the links to all of the class sessions and the links to the class session playlist. Okay, so that's the job right there. Good deal. Let's go back to week one. Okay, other questions I can nail down for you quickly. If you type it in the chat window and I don't answer it immediately, just hang on because I will answer it. I want to show you a couple things. If you, let's go back to my paper. If you have particular question numbers that you want to take, Like, how about 1.217? How about 1.429? Whatever. Again, throw them in the chat window and I will write them here and then check them off as we go through the session. Okay, good deal. So I got a handful of people here. So yeah, as I was saying, I'm going to go through the XYZ homework maybe later today or tomorrow for several classes. See who's in, who's not in. See what preliminary work you've done just to make sure it's behaving the way we want it to behave. And then we will make sure we help all of you get connected there. Thank you, Kayla. How many emails have I answered in the last 48 hours? All classes combined? Probably 8 to 10. The idea here is that you could certainly, as I said a second ago, you could certainly bury me in questions and never hear from me again. But I'd rather you try than not try. So send me your questions, even if sometimes my answer doesn't seem excellent. We'll check out a few of these. 20, excuse me. Thank you, thank you. Another thing I do when I write those down like that, if we do them on this paper, I'll cross them off. If we don't do them on this paper today, I will maybe put those at the top of my list for, you know, a video or something. Do I want the book number or the online homework number? If you have, that's a really good question. You know, book number is easiest for us to look up here, but let's say you came across a stumper in the online homework. You could screenshot and send me a copy of that screenshot in your chat window. And sometime later, you guys can test this. In your chat window in the lower left-hand side, where you type messages to people, there's a little button or something that says file. You could attach a file to the chat window, and then I would see it, you know, like you were doing some work and you didn't want to scribble it all in the chat window, say, you know, here's the problem I'm working on. You could literally throw it in the chat window. That would be one way of getting the online homework number to me. For online homework, I'd probably rather see a screenshot right now so that I don't have to dig up more windows on my computer while I'm trying to help you guys. So I'd say book number is a really good idea. If you got a stumper on the online homework, send me a screenshot. Also, though, you know, bear in mind, I'm letting you do the online homework. So, you know, while you're sitting there doing the online homework, don't fire screenshots at me to help you complete the online homework. But I know that's not what you're doing. Do you have a written assignment? Excellent. I'm just spending some time taking these questions here. So the more of these questions I take, the more you guys will get into the flow. So do we have a written homework? I will go to week 1. I will go to the homework button. And there you see all homeworks and due dates. So you had no homework due yesterday, of course. You only had one day. A week from yesterday, still no homework due. No homework due in the next week. It's an abbreviated holiday week. I will post sometime over the weekend or the beginning of next week a first homework problem for you. When it is posted, it will be a link right here. And then you'll just click that link and you'll see the problem. Like we tried to describe previously, it'll be just similar to a problem in the book. So answer, no homework problem written yet. Also remember that under, oops, wrong course. Under our resources page, again, click homework. You can see all the homeworks as they appear. Check the next question right here. No, super question. Both the written homework problems. Oh, okay, I got to make sure I read you correctly. You are correct. The XYZ homework is graded and the recommended problems are not. But down here, grading syllabus, your grade is XYZ homework. The written homework problems that I'll give you one problem a week approximately, then the 2 exams. The recommended problems are not graded. The reason the recommended problems are gold to you, very valuable, is because, you know, if I'm thinking about exams, I picked those recommended problems so that they would be the good representatives from that section. So if you're practicing for an exam, I think those recommended problems are certainly a good place to start. That's why I post solutions to some of them or post solutions on request. Okay, very good. Thank you, Trevor. Okay, we're going back to here. And I'll go back to my paper. So first of all, I'm just looking at my physical book right here. And I'm scanning a couple things to make sure that I can see your answers. Longest side of a right triangle. It's called the hypotenuse, no problem. Something was beeping at me, and I'm sorry if I missed it. I can guess what that was. My phone was beeping. It was from Zoom. Someone was trying to call in on a phone Zoom. I'm going to, if that was you, put a message to my email or the chat window, but it was probably someone who's not physically here, but I'll work it out. Okay, I'm just scanning the problems you gave me. Very good problem. I like 19, 17, 3, 20. Very good. 59. Very good. 59 is very good. And 63. 63 is a really fun problem. And I could give you some tip for doing that. That's true. It makes a very pretty picture. And back to 47. Perfect. Okay, so those are all questions right on target with what we're doing today. So at some time or another, I'm going to hit all those questions, three as well, but I underlined the ones that I thought were very excellent. Okay, 63 is 2, but it's kind of like a cherry on top of the Sunday question near the end. It's fun. Okay, when someone's saying 1.3, let me pop in there. Let me pop in there. Very good. Very good. Sam, you may have sent it to my email and it has not yet arrived. If you have the chance, try to attach it into the file in the chat window. If it doesn't work, attaching the file, tell me, because it's possible on my side I have to enable different file types. PDF certainly come through, but maybe it's waiting for a PDF. Okay, I don't have access to the XYZ homework numbers right now. So you'd have to give me ones that are in the book that are close. Okay, good deal, good deal. Good deal, then we'll get started. Just to cover this question, 2 textbooks? No, there's only 1 textbook, and this is it right here. And the link to this textbook is on our website. Now, maybe you're considering the idea that, like, here's a textbook and here's the XYZ homework. No, the homework is just the homework system, and inside that homework system, you have access to the book. Okay. Sam did manage to shoot up a PNG. So before we get started, I'm just curious what that looks like when that file comes in there. So let me open it and then share it with people, because this would be a great way to get some questions answered if that worked. Okay, so what you're seeing is an image that Sam just screenshotted to me. Let's let this represent the angle with a measure of such. Indicate whether the angle is acute or obtuse. Otherwise, choose neither. Got it. Okay, this is an excellent question. I'm going to keep this question on the screen, although I'll stop sharing this window. And then I will answer in a second, because this is one of the first things I wanted to review too. Very good. Okay. Okay, very good. Yeah, so now we got a pile of questions we could look at. So let's get going on the checkoff list I have here. And then on the way, we will pick off these questions. Okay. And as we get into the system, we're going to feel much more comfortable about, getting things going. So we'll be faster at this. First thing I wanted to do is bring some of the handouts to your attention that are linked to on our webpage. So let's look at the handouts that I'm listing right here. First, the handout angles, because that will cover that question that you just flashed on the screen to me. So remember, the handouts under week 1, handouts are listed right here. And the handouts angles that I specified on when you click that, you go to this list. Here's the handout angles. Oops, my apologies. I have to share that screen. Ta-da. Got it. So back to the start. Week 1, handouts. There's the first handout I'm measuring. All the handouts we're discussing are right here. Angles. And then when you click that, you can see the handout, or you go to this folder that has all these handouts. And here's the angles handouts. So just quickly, let me run through some of the things that are written here. And I do apologize in a sense if I'm reading and running through things that are pre-written. You don't want me to write and talk at the same time, because then we'd go at a snail's pace. But that means that you're going to have to be consuming these as well. So just basic angle terminology. The side that you start on is called the initial side. The side that you end on is called the terminal side. These are 2 half lines. People call them rays. And the point where the 2 rays begin is called the vertex. Now you can name an angle by naming the letters in the angle if you have points on those lines, like ACB. And when angles go counterclockwise, they're called positive angles. And when they go clockwise, they're called negative angles. That always sounds funny the first time people hear it. You could have a negative angle that goes quite far. And you could have positive angles that go more than 90 degrees or more than 180 degrees. When we talk about degrees, we're talking about 1 full turn being 360 degrees, 1 revolution. So that means 1 revolution is 360 degrees, 2 revolutions is 720 degrees. A half a revolution would be 180 degrees. And a quarter, that's a straight angle right here. It's kind of tiny. And a quarter revolution would be 90 degrees, 1/4 of the way around the circle. That's a special angle. It's called a right angle. 3/4 of a revolution would be kind of like the edge of a table right there, 270 degrees. So get familiar with where things are in the plane. The coordinate plane chops the paper into 4 pieces. And each of those 4 pieces are numbered from upper right counterclockwise. So first quadrant, second quadrant, third quadrant, and fourth quadrant. The angles that are 90, 180, or 270, those are special. They're not in a quadrant. When you talk about the 90-degree angle, which lies starting on the horizontal axis and ending on the vertical axis, that's not in quadrant 1 and it's not in quadrant 2. It's called a quadrantal angle. It's an angle on the quadrant. The paper that you flashed at me a second ago, when you said that the angle has a measure between 0 and 90, that's an acute angle. So I go back to that image you gave me a second ago in a minute, but it says if an angle is between 0 and 90 degrees in size, it's acute. Acute just means less than 90. And obtuse means more than 90, between 90 and 180 specifically. We used these words last time, but that's the rest of that screenshot you gave me. Complement and supplement. When you have an angle that's less than 90 degrees, its complement is the rest of the angle that makes up the 90 degrees. So if theta in this picture right here is 20 degrees, then the complement is 70. If you have an obtuse angle, such as you have the theta here is 100, then the supplement is the rest of the angle making up 180. So if theta in the second picture from the top right is 100, then beta making up the difference to 180 is 80. Those are supplementary. And this is how you're going to answer that question that they asked you on that sheet. So they wanted you to read this in the book, and you were to read this in the book. If your angle is between 0 and 90, then the complement of that angle, if your angle is 10, the complement's 80. If your angle is 20, the complement's 70. Really, all you got to do to find the complement is say 90 minus the angle you're given. If your angle is 30, the complement is 60. Same thing with supplement. If your angle is 20, the complement is 160. So I'm going to go back to that screenshot you shot at me. And if I could blow this up for you so it's easier to read. There, that's a little bit better. That's how I would answer this question. Let's suppose T is an angle. Let T represent an angle whose measure is between 0 and 90. That's between 0 and 90 degrees. Is that angle acute, obtuse? You choose. I guess I would choose acute too. Could it be neither? I suppose it could be, exactly 90 degrees. That's not acute and that's not obtuse. Give the complement and the supplement of the angle. They didn't tell us what T is, but we can still use the same logic. If T was 10, the complement would be 80. If T was 20, the complement would be 70. To do the complement, I just take that number and subtract it from 90. So the complement is 90 minus T, and the supplement is 180 minus T. If you want help on that question, you can check this video and this ebook. So I might be sparing on these questions that I ask from the homework system. You can shoot them to me if you're stuck, but I'll let you go to the ebook and the video to check first. Remember, you definitely want to read everything you can in the book before you try these. Don't just jump into them and learn while you're going, because it'll take you a long, long time that way. Okay. So talking about the handout angles. Let me show you the next handout I want you to review. These angle relationships and similar triangles. That's really, really important. So if I'm going to go back to our handouts page. Oh, excuse me. Angle relationships and similar triangles. Again, if I click on that, I get this page of, handouts that I've given you. Sometimes the titles go on for a longer time and they're hard to read. So I can make this list, angle relationships and similar triangles. These are some of the relationships I showed you last time, but I'm not too particular about all of these names. I just want you to see that if you draw two lines that intersect, then the opposite angles are automatically the same, whether you do horizontally or vertically. People call those vertical angles, whether they're horizontal or vertical. If you have parallel lines that are crossed by another line, it automatically creates lots of angles that are equal to each other. But the fancy words, I'm not so impressed by. When you have two parallel lines and a line cuts across them, it's called a transversal. But I'm never going to ask you a question like on a test, what's a transversal? So these are just the official names. If someone says alternate interior angles, then they're just trying to be very fancy and talk about angles 4 and 5 or angles 3 and 6, because those are the angles created by the transversal. And they have to match in size. They have to be the same size because all these lines are straight. We made a big point of this last time. When you have a triangle, doesn't matter what kind of triangle, when you add the three angles of the triangle, you always get 180 degrees. We just talked about the word acute. Acute means the angle is less than 90 degrees. If you have three angles, if you have a triangle with three angles that are smaller than 90 degrees, that's called an acute triangle. If you have a triangle where one of the angles is a right angle, it's called a right triangle. And if you have a triangle where one of the angles is obtuse, it's called an obtuse triangle. Other special triangles that you need to know, you could talk about side lengths. If you have a triangle that has three equal side lengths, it's called equilateral, just meaning literally equal side lengths. Of course, it would always have equal angles too. If you had three equal angles that added up to 180, each one of those angles is 60 degrees, right? Isosceles means you have two equal sides. And then you'll have two equal angles, but they could be of any size as I pull this vertex at the top up or down. So when you have three equal sides and three equal angles, the angles have to be 60 degrees each, but isosceles triangle, these two matching angles at the base could be anything. If you have a triangle that has no equal sides and no equal angles, you might kind of think that that's the boring case, or you could say it like this, it's the not special case. If you just ask someone on the street to draw a triangle. That's an interesting question. Would they draw a right triangle? But if you just drew a triangle randomly, you would probably draw something that doesn't have equal sides at all. Three sides, none of them the same. That kind of triangle is called scalene. It means no sides match and no angles match. Again, it's vocabulary. It's important to know those words, but I don't test you on the words. Here's a big thing for today. It's a concept called similar triangles. Similar triangles, if you allow me to blow that up, is just literally triangles that have the same shape. Not the same size, but the same shape. So you could have two triangles. One is bigger than the other, but your eye immediately tells you, oh, those are the same shape. The angle B looks like the angle E. The angle F looks like the angle C. Angle D looks like the angle A. If you have two triangles that have the angles matching, not the sides necessarily, but the angles, those are called similar triangles. Like one is a blown up version of the other. And when you do have similar triangles, you have a big, big advantage. The angles that correspond match, they have the same measure. And the sides that correspond have proportional lengths. That means, C is to F as A is to D. Corresponding sides have a proportional length. Or you could say F is to D as C is to A. You can form all kinds of proportions as long as you use matching sides with respect to the angles. So in there, I say C is to F as A is to D. Sorry. C is to F as A is to D, yes, as B is to E. That's one way you could look at it, making ratios between the triangles. Or you could make ratios among the triangles. C is to B as D is to E. Or sorry, C is to B as F is to E. Or C is to A as F is to D. Now, there's some type of quick talking we do when we talk about triangles. I talk about the angle E, or I talk about the side length D. When I'm writing these ratios, am I saying C is the name of the side, or am I saying C is the length of the side? Often we just put the two together anyway, because when I say C to F, I'm talking about a number ratio. So C to F, A to D, those are numbers ratios. So when I talk about side A, I could talk about the side A, or I could talk about A being 5 meters. You can talk about the length and the side almost interchangeably. Same thing with the angles. Here's angle B and here's angle E. And when I say B equals E, I don't mean the letters are the same. I don't mean the points are the same. I mean the angle at B is the same as the angle at E. That's what I made by these two comments. We sometimes write that the angles are equal when what we mean more precisely is that the measures of the angles are equal. We sometimes write that the ratios of the sides are equal when what we mean more precisely is that the ratios of the lengths of the sides are equal. So a lot of powerful information on there. Okay, next thing I want to do is use that on my whiteboard over here. So I pre-drew some triangles for you. And remember, I had a handout. Let me go back to the handouts. I had a handout called the exact values handout. And the exact values handout is like a speech to you that the 3 most famous triangles in the universe, at least the 3 most famous right triangles in the universe, are the 45-45-90, 30-60-90, and 15-75-90. And they're famous because it's easy to remember the ratios of the sides. What I want you to memorize, what I want you to get in your mind right now are these three triangles and the ratios of their sides. This table right here, we'll talk about later, not right now. Just focus on those three triangles and the ratios of their sides. So what I wanted to do was show you that on my whiteboard briefly. And the other day I was trying to mess around with whiteboard and laser pointer. Laser pointer looks really good in front of me, but on the whiteboard it's a kind of a dull red dot. So I don't think it really helps your attention very much. But I'll stand up and point at them if we need to. The idea that in a 45, 45, 90 triangle, I don't think I'm going to do this very often, but maybe I will stand up. In a 45, 45, 90 triangle, you bet your money that these two legs are always the same length. But the thing that's beautiful about that is the similar triangles, the scaling. If this is 1 and 1, then by the Pythagorean theorem, this has to be the square root of 2. But if this is 17 and 17, this is likewise 17 times the square root of 2. All you have to do is scale the number. If this is 12, then this has to be 12, and this has to be 12 root 2. So that's what's extremely powerful about these three famous triangles. Let me try it again. In the 30, 60, 90 triangle, short leg, long leg, hypotenuse. The hypotenuse is always the longest side in the right triangle. And you like to remember this because of the 1. The hypotenuse is always twice the short side, and the long side, the long leg, is always root 3 times the short leg. But do you see what that means? That ratio holds for every 30, 60, 90 triangle. So if this was 12, then twice 12 is 24. And if this is 12, then root 3 times 12 is just 12 root 3. So if I give you any 30, 60, 90 triangle and name one of the sides, you automatically get to name the other. Let's say that's a 30, 60, 90 triangle. And it's a right triangle. So now I've told you 30, 60, 90 triangle. If I say that this is 7, you don't have to calculate. You don't have to think about it. You just label the other sides. Twice 7 is 14. 7 times root 3 is the length of that leg. There's no calculating. If you remember that ratio. Let me try it again, harder. If this is 6, can you name the other two sides? This has to be half of 6. This has to be root 3 times 6. Root 3 times this. Let me try a hard one. What if this was 10? What if that long leg is 10? This is the hardest example. You try to get to these other two legs, this leg and this hypotenuse, excuse me, and you're kind of stumped because you need directions for going from there to there. What are the directions? The directions are written on this triangle. The directions for going from long leg to short leg are divide by root 3. And that's the directions for every 30, 60, 90. And that's all you have to do is divide by root 3. What are the instructions for going from here to here on a 30, 60, 90? That's the easy one. Double it. Okay, double 10 over root 3. 20 over root 3. That's why I'm showing you these triangles. Because if you master these three triangles, you've mastered any triangle that has the same shape. Now let's look at the weirdest one. And by weird, I mean very rare to find this printed in any book. But I kind of like it because 15, 30, and 45, they go together. They're kind of like 2 times 15 is 30, 3 times 15 is 45. This ratio is very funny looking, but I tried to show you the poetry of it last time. I don't know what root 6 minus root 2 is unless I ask a calculator. I don't know what root 6 plus root 2 is unless I ask a calculator. But if you check this out with a 15-degree angle, if you measured this out carefully, whatever that number is, that's the ratio of these three sides. If this is a 4, then this is root 6 minus root 2, and this is root 6 plus root 2. If this is an 8 on a 15, 75, 90 triangle, this is twice 4, then this will be twice root 6 minus root 2. And this will be twice root 6 plus root 2. But remember, I don't know those numbers off the top of my head, but I know where to go to get them. Let's try a weird one. What if this was 45, I'm sorry, what if this was 15, 75, 90? And I put a 2 here. Can you label the other sides? Well, that would take some fancier work, but let's think about it. How do you get from this side and turn this side into a 4? You know, if I have root 6 minus root 2, and I want it to equal 4, what do I do to it? It's kind of a trick question. But if I want to turn this into 4, I have to multiply by 4 over root 6 minus root 2. It's kind of a brain teaser. But if I multiply this by this, I get 4. What does that mean? Multiplying by this number is the instructions for going from here to here. So if I want to go from this to this, all I have to do is multiply by 4 over root 6 minus root 2. So if this side is 2 and I multiply it by this, I get 8 over root 6 minus root 2. That's what this side has to be. Now, compared to these two triangles, you know, this is kind of goofy. You got to think carefully about it. These, in comparison, seem mellow. But it's really important that you get these relationships. How do I go from here to here? Well, to go from here to here, I have to divide by root 6 minus root 2. And I have to multiply by root 6 plus root 2. That's how I turn this into this. It sounds strange, but it's true. If I multiply this by this, I get root 6 plus root 2. What if I want to change 2 and see what happens there? I still multiply by root 6 plus root 2 over root 6 minus root 2. And when I multiply 2 by that, I don't like what I get. It's really ugly, but I know it's correct. Now that's the advanced triangle. That's the crazy triangle. So you got to get used to that one. That takes practice. These two you can do faster. Start by memorizing these two. Now, I'll work more with you on the 1575 90 later. But sometimes it's valuable not to put a number here, but to make that a 1. See, I put the 1s where I like to do them, made the calculation easier. Sometimes to compare all 3 triangles at once, you want the hypotenuse to be 1 in each case. So let's pretend I made each of these the same length, hypotenuse-wise. They're not quite the same length. Well, then what would the other sides be? If this was a 1, I divided by root 2. So these would be 1 over root 2, 1 over root 2. And remember, by rationalizing the denominator, 1 over root 2 is root 2 over 2. Multiply both top and bottom by root 2. If this is a 1, then I must have divided that number by 2. So I divide these two numbers by 2, 1/2 and root 3 over 2. And this is not so bad there. But if I change that 4 into a 1, I've divided by 4. So I divide the other 2 by 4 also. Let me get this off your screen. So I don't care what you have to do. Memorize it, write it on a piece of paper and swallow it, tattoo it to the back of your hand. Well, okay, I'm not much for tattoos. But if you're going to get a tattoo, why not get a good tattoo? Why not get a useful tattoo? Know these triangles by heart. Any version of those triangles. And then you can use the fact that similar triangles are the same triangle scaled. You can use that to name thousands of triangles. Okay. I don't know how that came off. And I'm not going to know how that came off until I look at the recording later. So I will, and I see some questions that you launched into here. I'll try to look at that. Zooming in on the screen, you might be able to do that better because you're kind of controlling your screen. So you can click on any of these little TV screen icons in your Zoom window to change screen. And you do that in the gallery view or in the speaker view. Up in the upper right-hand corner, there's a little tic-tac-toe board that says gallery view or speaker view. Okay. This is going to hurt me, but give me feedback on that whiteboard debacle. So I don't want to stand in front of the camera and just yell at you. But if the whiteboard was decently helpful right there, then maybe on some other time I'll use it in the same way. You can throw that in the chat and you won't hurt my feelings. Okay. So it's really, really important to know these exact values. And they are on this sheet. And another thing, I made a note for myself to tell you, like, I know everything's online. I know you can click and find anything you want, and probably stuff that's a lot better than mine. But I'm saying after you look at one of these handouts, if you can print it, if you have access to a printer, print it out. Just so you could put it in a notebook, just so you could hold it in your hand. Because on your computer screen, you see one thing at a time, right? But if you're doing some work on your table in the kitchen or something, you could have 2 or 3 of these handouts open in front of you. Now, what's written here in this table, I'll tell you about later. Maybe not today, maybe towards the end, but this is not exactly what we're doing today. But if you know these triangles and their ratios, it's like having a math superpower. Okay. Now, next step. And then we're going to get to use these down here in section 1.3. That's the note that I made to myself there. I was going to tell you to consider printing these out. Also, here's another useful handout. It's in your folder. It's called the unit circle. We're not ready to consume that yet, but I will show it to you. The unit circle handout is a handout where I gather a lot of this information together. I don't have a link to it on the site yet, but if you go into the folder with the handouts, there's one called the unit circle. And this example, I'll blow it up, is in the end why you want to see every 15 degrees. If you think of a circle as being chopped up into 90-degree parts, that's 4 equal parts. 45-degree parts, that's 8 equal parts. But you could also think of a circle, 360 degrees, as being chopped up into 15-degree thin slices of pizza. And when you do that, it's going to make it much easier to remember the numbers we're going to use. Don't worry about the names and the numbers yet, because I haven't covered this. Well, today we will, the famous words sine, tangent, cosine. But this handout will help you put it all together and remember it. So check that handout out. I'll name it and link it later. Okay, back to work. If you've looked at section 2 yet in the book, first you do a double take and you say, what do you mean equations and graphs? What do I care about lines, parabolas, and circles? That was the last class. That was the algebra class. Well, he wants to refresh your memory, and he wants to remind you that equations always make graphs, and graphs always make equations. And let me pop to Desmos, because this would be really useful to show you in Desmos. Go back to my web page and just open another tab. Desmos.com. Remember I said you could create an account if you wanted to, but you don't have to. You can just graph. And let's say for a second, and I don't know if I can do this on my screen. No, I can't. I wanted to hide the graph part, but I guess I don't get away with that. But let's talk about an equation. Y equals X. And you see what Desmos did? It automatically gave you a line. Maybe you have some experience with lines, right? What is this line? This line is the collection of all the points in the plane that satisfy that. What if I told you to, I don't know, solve y equals x? You remember back to your algebra days? What does it mean to solve an equation? To solve an equation means to tell me the numbers that make it true. If I told you to solve x minus 2 equals 0, there's only one number in the universe that makes that sentence true. But if I say solve y equals x, there's lots and lots of numbers that make that sentence true, like 1, 1, and 2, 2. And, negative 17, 17. How about pi, comma pi? That's getting a little bit weird. Pi is, we'll come across pi later. Anytime I have the same coordinate in x and y, this sentence is true. Get somebody popped in here. There you go. Welcome. So he wants you to remember, let me see if I can make this a little bit larger. Slightly larger. He wants you to remember that every time you write an equation, you are really drawing a picture. Even x equals 2 can be drawn with a picture. It's just a very boring picture. It's a single dot on the x-axis. But you know, as you change this equation, y equals 2x, you get a different line. Now these points don't work anymore. Let me get rid of them. How about subtracting 2x from both sides of this equation? You get the same line I had a second ago, right? Do you notice that these two lines are the same? Whether it's green or red. Fun thing to do in Desmos is use a dotted line. Now that kind of shows you the dotted green line and the red line at the same time, but you can play around with Desmos. But really, very seriously, every time you write down an equation, let's do a crazy one, you draw a picture. This red curve is a picture of the equation x times y equals 1. What happens if I square the y? Now this is a picture of x times y squared is equal to 1. That means every point that makes this sentence true is on this red curve. You can actually click in Desmos on the curve and see the points. Now, it's definitely approximating, but if you took 1.384 times 0.85 squared, it's telling you you're going to get very close to 1. Let's try it. 1.384 times 0.85 squared. Now you see that that's not the same as 1. That's probably because I was rounding off right here. Well, probably because the machine was rounding off. But if I had more decimal places, I bet I'd get closer to 1. So he wants to plant this idea in your mind that every curve is made up of lots and lots, millions of points. And so now that you're ready to accept this, let's go for one of the most famous curves in history. Not x times y squared. Let's not do that weird. Let's go x squared plus y squared. This is a circle. It is a circle with a radius of 1 unit. Let me zoom in a little bit. This says, I am all the points that when you square the x and y coordinate, you always get 1. If I took those two numbers and squared them and added them together, I'd be equal to 1. X is 745 and y is 667 negative. Let's try it. X is 0.745 and y is negative 0.667. I don't want to graph them. What happens if I take those two numbers, copy, paste, square, plus copy, paste, square. Now, I got to put parentheses around that to make sure I square the negative sign. See, again, it's not 1 exactly. Why is it not 1 exactly? Because I can't exactly be, you know, the calculator, computer is rounding things off. That's what happens if I put a 4 here. Does the radius of the circle become 4 No, the radius of the circle is 2. Why is that? Because we know this famous relationship, x squared plus y squared equals r squared. Here's a really cool thing in Desmos. You see how I typed the R and the computer kind of said to me, first of all, you got the danger signal here, right? Danger signal means computer does not know what I'm doing. In fact, it even tells me, you have too many variables. Tell me what R is. And then it gives you a suggestion. Do you want to add a slider for R? If I say add slider, look what happens. I get this green thing that creates circles with different radiuses. Let's try a radius of 9. Let's try a radius of 3. The radius is 3. This is x squared plus y squared equals 9. Let's try a radius of 4. Then I get x squared plus y squared is 16. Okay, why do you need to know the equation of a circle? Oh, by the way, let me zoom out. This is a kind of a boring circle because it's centered at 0, 0. What if I wanted the circle to be centered at 1, 1 on that black dot? All I'd have to do is subtract 1 from x and subtract 1 from y. Excuse me, I'm having trouble manipulating the keyboard. Check that out. Now I have a circle centered at 1, 1 with a radius of 4. I can still change the radius, but it's centered now at 1, 1. What if I wanted the circle to be centered at -2 and 3, right there? I do the same thing, except be really careful. I would subtract these two numbers from the x and y. But remember, subtracting -2 will be saying x plus 2. Let's try it. X minus -2 is x plus 2. And then y minus 3 right there. Now I got a circle centered at -2, 3. And I can change its radius as I want. I wanted to pop into Desmos today because I wanted to give you this mission, this speech. The calculator is wonderful. I like your calculator. You could draw some good things on your calculator. When you play around with Desmos, you can draw some fantastic things and you can animate them, even much more than this. So play around with Desmos a little bit when someone asks you to graph something, and we will. I'll show you the calculator too sometimes. But Desmos has got this extra feature of animation, a lot more flexible. Calculator's got more calculating juice. I mean, the calculator can calculate a lot of things Desmos can't, but not so many. Desmos is pretty powerful. But as far as graphing, drawing, Desmos shines. Okay, I'm going to pop out of there. So look at the problems in 1.2 as a refresher from your algebra course. And remember that the most important graph for us is a circle. So if I draw the circle x minus h squared plus y minus k squared, I'm talking about a circle that's centered at a point h and k and has a radius of r. Now that's why I use the Desmos or calculator, because I can't draw a circle worth anything. Okay, now we're ready for the big payoff this week. And this is what you got to practice. And we're going to practice it some more in the next week. So if this is too quick, don't worry about it. First of all, equations and graphs are the same thing. That's what he wanted to remind you of. Okay, one more mission today. And this is related to this handout. This handout is called Fundamental Trigonometry Identities. This is what we're doing in this course, trigonometry. Remember how I defined trigonometry for you last time? 3-angle measurement. Try, 3, gone, literally angle in Greek. I'm not good at Greek. And when you say metry, like geometry, trigonometry, you're measuring something. Metr is like Latin, Greek word root that means to measure. And you get the same thing when you say meter stick. Or in science, there's a field called metrology. Metrology is the study of measuring. So trigonometry means 3-angle measurement. And our goal is to be so good at measuring angles that we can find ourselves from any place in the plane to any other place in the plane. So now we're going to make this speech. Let's say you have an angle, and the angle has a beginning side on the positive x-axis, and it stops somewhere over here in the second quadrant. That'll be the terminal side. Let's call this angle, you can call it anything you want. You can call it, puppy if you want to, but traditionally people name angles with Greek letters, and the most famous Greek letter for angles is theta. Sorry, I'll center the picture. In the back of your mind, whenever you see an angle like this, and this is the connection to the triangles that I had on the whiteboard. Whenever you see an angle and someone names a point that sits on that terminal side, I don't know what this point is. I'm not counting boxes, right? Let's just call it X and Y. Then what you should see here is a kind of a ghostly triangle, and maybe not even a ghostly triangle. Think of a right triangle. Right triangles are the most powerful triangles. Think of a right triangle that sits on the x-axis. Always sits on the x-axis. And why do I love right triangles? I love right triangles because it's easy to describe how long their hypotenuse is, right? That's literally the distance formula. But I want you to think of this as not just the distance r. I want you to think of it as reminding you of a circle. I mean, literally, I could draw a circle here of radius r. I want you to think of that as the Pythagorean theorem in a really important way. Distance and circles and the Pythagorean theorem are all the same thing. And that's why we started last time talking about the Pythagorean theorem. So here's a triangle that stops at that point and has a radius r. Now let me give you, for example, just so you can attach numbers to it. Let's say that in the second quadrant, now in the second quadrant, the x value would be negative, right? So let's say x is -3. And let's say y is 1. I'm not trying to draw perfectly. I know that doesn't look like 3 to 1. But what I'm saying is, let's pretend this length is 3 and this length is 1. Then I know you could tell me what r is. Well, 3 squared plus 1 squared is r squared. 9 plus 1 is r squared. r squared must be square root of, must be 10, so r is the square root of 10. Always think of r as positive number, not negative. So if x and y are -3 and 1, then r has to be root 10. Now think of these three sides of this triangle. You know, some people write -3 here, and I don't mind too much, although it's better to write 3. -3 is the direction I'm going. 3 is the length. But let's think about this green triangle. Let's think about this angle theta. In both cases, I'm interested in these ratios, the x, the y, and the r. Just think about those three letters, x, y, and r. How many ratios can you form out of those three letters? Well, x to r, y to r, r to x, r to y. If you made up all the ratios you could make, how about y to x and x to y? Think about these ratios. These ratios are all the possible ratios I could make out of that triangle that I can make out of this angle theta. And these 6 ratios are called the trigonometric ratios. Let me see if I can get everything on the board at once. Sorry. The trigonometric ratios. And literally, in Greek, it's the ratios that measure the 3 angles. With these ratios, I can measure the 3 angles in this triangle. They have famous names that are kind of buried in history, but I'll remind you why they got these names another point. The first is called the sine. When you take the ratio of x to r, you are forming the sine of theta, not the sin of theta. We abbreviate with 3 letters, but it's called the sine of theta. When you take the ratio of y to r, you're forming the cosine of theta. When you take the ratio of y to x, you're forming the tangent of theta. You always abbreviate with this first 3 letters. Well, in this case, you abbreviate with the first 3 letters. What about these other 3 ratios over here? Do you notice that they're all reciprocals of the ones that I wrote to the left? So the reciprocal of sine is called cosecant. It's abbreviated CSC theta. The reciprocal of cosine is called secant. Well, I'm pronouncing it too slowly. Just say secant. The reciprocal of tangent is called cotangent. Cotangent. You don't have to pronounce it slowly. What you're going to do with these is magic, and it's going to last for the rest of the course. But these 6 ratios will allow us to measure any triangle, not just right triangles, but any triangles. So in section 1.3, he wants to make you practice that he gives you an x and y, you draw this triangle, you find the r, and then you name these ratios. He says, well, what's secant? And you have to read it. Let me give you an example. If secant of theta, that's the secant of theta, if the secant of theta is 3/2, what is the cosine of theta? And let's assume that theta is in the first quadrant, quadrant 1. Let me draw a picture. Secant is what? R over Y. So I want to draw a picture of an R that's about 3 to 2. I want to draw a picture of an angle, of a right triangle that has a ratio of R to Y is 3 to 2. But you see, as soon as I name those two numbers, I can name this third number with the Pythagorean theorem. 3 squared is 2 squared plus x squared. Well, if 9 is 4 plus x squared, then x squared is 5. That means x is plus or minus the square root of 5. It could be x is over here, minus square root of 5, but I said I was in quadrant 1. This is root 5. Now, what's the cosine of theta? Now, that's a trick question in a sense. Go back to this chart. If the secant of theta is r over y, notice the cosine is y over r. So as soon as someone said, what's the cosine? I could have said 3 over 2. Becomes 2 over 3. But you see, I can also name all the others. What's the sine? Sine is x over r. Root 5 over 3. What's the tangent? The tangent is y over x. 2 over root 5. What's the cotangent? Well, it's the reciprocal of the tangent. What's the secant? That was given to me, 3 over 2. What's the cosecant? Now you got to remember these ratios. Cosecant is the reciprocal of sine. So if someone asked you for cosecant, then you just flip over sine. This is a game. This is the game of section 1.3. Your game is, if someone named two sides of a triangle, could you name the third if I told you what quadrant it was in? And then if you've labeled the triangle correctly and you know the point, X and Y, depends on the quadrant as to what these signs are, then can you name the 6 ratios? Now we're going to call it quits for today. And I got to practice this a lot more with you, and that's the subject of the next section. Block out the part about what the crazy names are. I'm not worried about what the crazy names are. You'll get used to the names, but practice playing this game. Practice playing this game of figuring out the ratios of the sides created by a point on an angle, created by this right triangle. Okay, let me go back to this paper right here. When some of you were shooting these questions at me, I think you pointed out some of you were shooting questions from the XYZ homework. So these are not book questions. And I'm not going to produce videos or answers using these book ones, but I might add a few of these. So thank you for diving into 1-1. You keep working on it, but remember, read the book, practice some problems out of the book, then you can dive into the homework. So I might try to post some answers that are similar to these problems or the actual book problems. Maybe I'll show you some more examples like this. I think on my website, I have a couple problems showing you how to do this trigonometric ratio game. Okay, basically, even if I talk too much, that's a great deal of our time today. I'm going to look into the homework, XYZ homework, see how you guys are doing. You can send me the questions and I'll post some answers or help you out inside the homework. Get inside the homework, keep practicing. We won't talk about a written homework till next week after you come back from the holiday. So I don't know, whatever you can do with your weekend nowadays. You know, you got an extended weekend, so Stay safe and reasonable, but have a little bit of fun. I'll talk to you next Wednesday, 1 week from today. No class on Monday, September 7th. Have a good weekend.